All right. So this is we're closing out week 10. 10 and 11 is internal flows, pipe flow in I guess by other definition. Week 12 is external flows, and week 13 and 14, but really is just week 13, which is after the Thanksgiving break, is open channel flows. And so we talked about these are kind of the sharp end, I guess, of fluid mechanics, the practical aspects of everything that you've learned gets to be put into these formulaic approaches to be able to define systems. The systems, I guess, that you would work with would be things like pipelines, which of course bring natural gas to our households in the morning and spread it around the country from the Gulf and also from now in the Northeast in shale gas country to these population centers. But I guess other more interesting uses of pipe flows would be the jet lev stuff, which we've looked at before, which I think is kind of interesting. I think I mentioned before that one of these things had actually made the journey to Catalina Island, from LA to Catalina Island. And so if you ever fly into LAX, typically if you fly out, you fly westward, take off over the Pacific, and you fly off over Catalina Island. Maybe it's 5 miles offshore. It features in the movie Chinatown, a classic movie with Jack Nicholson. Certainly someone before your time, before my time for that matter, but it's a classic movie. And I have no idea where this is, but it's kind of an interesting application of these boats. So you see it's kind of like a jet ski, but it's really a pump, I presume, with an umbilical coming out of this trailing trailer, which pumps fluid at pressure into the pipe, and then can be directed by by squirting it downwards to be able to provide enough oomph to be able to keep you up. And I guess this is a bit different because I can't quite see, but it looks like it's coming out of their feet as well as out of their arms. Yeah, it is. So you see there. So it's kind of cool. And this is going underwater with it. Yeah, there's no reason why you wouldn't go underwater with it, of course. It just seems kind of bizarre to do it. So I think it's a pretty cool thing. So go out and buy one of those with your first paycheck when you get out of this place, instead of paying it to Penn State, which I'm sure you're more than happy to do. It's cost of business, right? In some respects, gives you a qualification. So anyway, so that's the deal. So I think that's all I had in this. I'm not sure what the other things I had on this video. On this one was gas spewing Icelandic volcano. Yeah. Well, a few years ago, Ekjufell was the volcano that stopped all the air traffic coming out of Europe because of spewing ash in Iceland. And I guess a volcanic conduit is a pipe that's just pulling different fluid, magma, through the earth up to the surface. So it's just a different form of pipe. So that's kind of where we are with this. So just thinking about it. All right. So you've seen this. You're probably very tired of this, seeing this all the time. But yeah, okay. So we've been talking about pipe flow, and so I guess there's a few things. It's probably worthwhile just reiterating and recapping exactly what we're talking about, because it's kind of a central theme of this class. If you looked at the review session for the third midterm, 2 of the questions are on pipe flow, and so it's something worth one question on dimensional analysis, week 9, and 2 questions on pipe flow. And so it's worthwhile, for obvious reasons, related to your career, but also related to this class, to understand exactly what we're trying to do. We've made the point before that really what we're using is the energy equation, which is Bernoulli equation. If we write it again, and I'm sure you're maybe tired of this, but all the same, it's worthwhile doing, is defined in terms of upstream, a pump head, and this being equal to the downstream components, which would be these. And the important terms for us are really these two individual terms. So one is the head losses, which are the major ones, and the other one is the head losses, which are the minor ones. And so I think what today we'll do, we'll talk about these minor losses, which are these. We've already talked about pipe flow, and then we'll do some examples. I think we'll get far enough along to be able to do that. And we can define all of these individual components. So the pump head is equal to maybe the unfortunately defined W, because we've used it for velocity, power, divided by the mass flow rate, rho Q, multiplied by G, gravitational acceleration, always the case. We can always get the head losses, as we talked last time, as being equal to typically a friction factor, which we have to define, the length of pipe times its diameter, and the velocity squared over 2g. Importantly, we made the case, and maybe I'll make this a bit more interesting than by doing it in terms of our, it's not meant to be do people still play hangman these days? Yeah? Okay. So this is kind of a hangman, but not quite. Not really, actually, is it at all? But anyway. But you get the idea from this, is that this is coming out, so this would be 1. This, of course, would be the water on both sides. And just to put some numbers on this, 2, 3, 4, and 5. And so in this, I guess, this equation, we have to do it from upstream to downstream. So I guess we need to know that this is upstream. This is downstream. Probably I would be interested in doing this as this, right? If I was solving this problem. And so these individual components, the sum, this would be the sum of the head losses. The sum of the head losses would be the components between 1 and 2, 2 and 3, 3 and 4, and 4 and 5. So I guess the sum of the head losses would just be equal to the friction factor 1 to 2 times the length 1 to 2 over the diameter 1 to 2, the velocity v squared over 2g. And of course this would be the velocity between 1 and 2, not the velocity either at 5 or 1. It might be one of those. And of course we could get that velocity is going to be equal to q over area. So we can always figure out what the velocity is if we know what the velocity in at velocity 1 or out of velocity 2, the flow rates would be constant throughout the system, and so we could calculate this from knowing what the velocity was. Typically we'd know what q is, so we could use that to calculate that velocity 1 times a1 equals velocity 2 times a2, etc. And so I guess this would be, in our terminology, velocity 1, 2 would be equal to, would be equal to some constant flow rate. So, and this is much too complicated for an exam question, so don't understand it for the fact of understanding it more than anything else. And so you'd sum up these individual components, so it'd be the friction factor between 2 and 3, the length 2 and 3, the diameter 2 and 3, times the velocity 2 to 3 squared over 2g, etc. So I guess there'd be 2 other terms there, right? You can guess what those are. So that's what this term would be. Likewise, the sum of these are the major losses. The sum of the minor losses would be some coefficient, k sub l, times v squared over 2g. And so this would be KL, I guess it would be 1 V1 plus KL joint number 2 V2 squared over 2G, etc. I guess the final one would be 5. Etc. Right? And so you just end up cumulatively adding these. And so this one, I don't really want to kind of overprint it, but that would be this one here. And so the deal is, if you know what the velocity going through the system is, or the flow rate through the system is, or the flow rate that you want, for instance, then certainly you know what all the velocities are at points 1, 2, 3, 4, and 5. You know what the velocities in each of the pipes are if you know the cross-sectional areas. And so all these velocities are known. And I guess what you would want to know as a result of this, I guess you would know that the pressure at point 5 is equal to 0 because it's atmospheric. I guess you'd know the pressure at point 1 is equal to 0, or a small number, right? Because it's underwater, but a trivial amount. So that's essentially atmospheric. So you'd know this, you would know this, you would know the height you want to be is a couple of meters, probably, between the nozzle, I guess, that's attached to you. And I guess the only other thing that you'd like to know would be this term here. And so you could calculate what the pump magnitude would be. And that's typically what would be interested in doing. So that's kind of a flying at 35,000 feet view of what we might want to be able to determine. So these things rely on two items. So one is that we need to know what the magnitudes of the major losses are. And I think we'll do an example about that today as we go further on. But not to bore you, remember that what the major losses are best defined by this Moody chart. It's a log chart. This is friction factor on one axis. This is Reynolds number, which is equal to velocity, density, a characteristic dimension, which is the diameter of our pipe, and viscosity, ratio of inertial to viscous forces. This is equal to an Euler number, which is a change in pressure divided by rho velocity squared. And we know exactly what the form of this is. You know, we looked at it yesterday. This is the chart here, but easier than looking at that. The characteristics of it are exactly this, that there's a transition from laminar to turbulent. This happens at about 2,000, Reynolds number of 2,000, 2 times 10 to the 3. This is laminar. So this is the deck of cards being scooped over each other. And in terms of these components, in the laminar regime, the friction factor is a function of Reynolds number. It varies with Reynolds number, I guess inversely. And in the turbulent regime, it's constant with Reynolds number. And so we have all these lines, which are these things here, if we simplify it anyway. And I guess there is kind of a no man's land, no person's land in between, where it goes from laminar to turbulent, but let's not worry about that. And these are indexed in terms of roughness. So big roughness at the top and little roughness at the bottom in terms of this. And so these change the way that we solve the equations because this is a function of velocity, right? It's a function of Reynolds number. So this friction factor is a function of velocity here. This friction factor is independent. So we solve in two different regimes. So we'll come back to that in a second, right? So those are the essential components of this chart, which we'll do an example of. Bless you. So the second one is that we have minor losses. And so I think, major losses are that HL equals friction factor, length over diameter, times the velocity squared over 2g in the fitting, in the pipe. And so this is length of the pipe, this is diameter of the pipe, and this is this term here. I was going to say something, but I've forgotten what I was going to say. Doesn't matter then, obviously. And the minor losses, these are obviously for flow within pipes. Length, diameter, and roughness. This is epsilon is the, I think it's the amplitude of this, epsilon. And so for minor losses, they're referring to flow typically in fittings and bends. It's not a bad drawing. And again, it would be a flow velocity in that fitting. And typically, it's equal to a loss coefficient, K sub L, times the velocity in the fitting, divided by 2G. And so if you happen to know the flow rate that you want in this system, so if you happen to know, for instance, what Q1 is, this would also be equal to Q5. Right? So this actually wouldn't be an arrow. By continuity, this would definitely be the case if we're not accumulating something somewhere in here. So what comes in here goes out, so the flow rate through each of the parts is the same. And so if that's the case, then we can certainly define the velocity and figure out exactly where we are on this graph, and then use that term in here to be able to solve for all of these. So presumably we can solve for all of these because we know the velocities and the friction factors. We can solve for all of these for the same reason. We can link, if we have a flow rate, we certainly know what V5 would be and V1 would be because of this. And as I say, the only thing we don't know is the power. So you can determine whether you need a 1 horsepower or 10 horsepower motor to go in the pump. And these are just relate to the individual, the corners within the system. So there's a whole, not really a science behind it, but the losses that we have that are local, so the minor losses are the ones that occur at individual locations, and they occur due to all kinds of things. And so we would have those in this particular case at locations 1, which would be entry losses, location 2, which would be a bend loss, 3 a bend loss, 4 a bend loss, and 5 would be an exit loss. I guess we'd have probably a pump HP in here. It doesn't really matter where it is. If you're writing this equation between upstream and downstream and it's locations 1 and 5, it could be anywhere in here, of course, but that's obviously the logical location for it. And we just need to account for those individual values. And so perhaps we'll spend a little bit of time talking about what they are. And so entry losses would be where you get flow entering into a system. So this could be into the pump that is sitting on the water's bottom. I guess it would be perhaps sucking it up from underneath. And surprisingly, there's a loss there. The loss is due to the fact that initially water is sitting at 0 velocity in this big tank, the ocean, and at some time it's sucked into here and it's going at some velocity which is not 0. So clearly between here and here it has to accelerate, and that acceleration takes energy, and F equals ma requires that energy is taken up in some way. So if we think of the loss coefficient as being this value KL times the velocity squared over 2g, obviously the velocity that we'd use would be the velocity in the pipe, not the velocity in the sea, because that's 0. And not surprisingly, this number is largely between 0 and 1, and it's indexing the effect of this acceleration. It's really allowing us to calculate dv dt, right? This is acceleration. So we can also think of this as mass times velocity squared, because we can write this differential as a v squared, right, instead of v, just by using, we've done it already in this class. And so I guess the only point to make here is that the more extreme the acceleration, with this kind of complicated entrant geometry, the larger the loss coefficient. And the smoother you make this transition to be able to give it a smooth acceleration from far out to right in the pipe, then the magnitude of this loss coefficient can change. So it's great, of course, if it comes out to be trivial, because if it's 4/100ths of a unity, then it's perhaps a number that you can ignore. And so you'd like, obviously, if you want your system to be as efficient as possible, to have this rounded out. I'm not sure I've ever mentioned the word vena contracta. I certainly did in one of the free jet exam question. Vena contracta is where you get some kind of constriction occurring just by the rate, the flow. So any flow coming into this fitting is trying to move around this corner. Since it's moving downwards, it would like to keep on moving in the vertical direction rather than turn this corner, just like a car going around a bend. And so there's a zone in here that might have stagnant fluid in it, not because it's an actual portion of the pipe which is solid, but because it just skids around the corner and there's no fluid. It's just filled with fluid, but that fluid is not moving. It skips over the top of it. And so you can get those effects in entry into a pipe, and that can give the fact that it would give an effective diameter of the pipe which is reduced, and so the magnitude of the loss coefficient is larger here because it's squeezing through a smaller area, and therefore it's going faster here than ultimately it's going in the rest of the pipe. Now, this cross-sectional area is some number, this cross-sectional area is less, so since the flow rate through here has to be constant, then this velocity has to be larger. And so you can calculate what those would be. I think the reality is in this class we won't use this very much, just because I think it's a bit tedious, but these are the realities of it. And of course you can characterize these things by just taking a pipe into the lab and measuring them experimentally. So we have entry losses by stuff going into pipes. You shouldn't be surprised that when it comes out of pipes, it would have exit losses. This is referring, I guess, not so much to it coming out of the nozzle of the jet lev, but going out of the nozzle and into a stagnant tank. And of course, that means that you have something going at some velocity here, and at some location here, it's going at zero velocity. And so, again, it seems to be, for some reason, not sensitive to that, but these values are always close to 1. And so that's kind of curious. I'm not quite sure why that is. But obviously it's going close to 1 because it's going at some velocity, and now it's going at zero velocity. So it's losing all of its momentum, and a loss coefficient of 1 means that the v squared over 2g term, this term here, is essentially being fully realized. It's going from some velocity to zero velocity, and so this term indexes that by being, if there's no loss, it's 0, and if it's a full loss, it's equal to 1. So I guess that's probably worthwhile noting that KL is typically, not always, greater than 0 and less than 1. So that's, and of course, you'd like it to be a lot less than 1 for your system to be as efficient as possible. You can talk about diffusers, things going into diffusers and going out of them. They're not the same, even though they look as if they'd be symmetric. Typically, for the reasons we talked about, these are always closer to 1, and these may be less than that, because obviously this is close to being this, right? I guess it would be close to being this. It just happens to be that it's a tank that somehow is truncated, so it can't come from down here and up here, it has to come along here. And so for a variety of different geometries you can look at these. You can figure out exactly what they are. You can, I suppose if you rationalize it, you can define what these loss coefficients would be and plot them in some way. So if area 1 over area 2 is equal to 0, that means this is small and this is huge, essentially coming into an open tank, and so we shouldn't be surprised that the loss coefficient is 1, because that's what we just described when going into a tank here. And we shouldn't be surprised that if this ratio is equal to 1, then this pipe is the same diameter as this, and it's equal to 0. And somewhere between here, it varies in some form, which we could define. We can also define it if these are angled. I'm not sure why this goes up to be greater than 1. I'm not sure what the rationale for that is, but probably we don't need to worry too much about it, but it has some interesting behavior. The other loss coefficients would be so the acceleration, v squared over 2g, you know that you think of this as being a constant velocity around here because the flow rate is constant, but of course velocity is equal to both speed and direction. And so if it's changing direction, as in going around a corner, then you have to apply extra force to be able to get over inertia. And so going around bends has some influence as well. And so I'll just go to this table. And I think we looked at this table already because I already today took some of the writing off it. But you can imagine that if you have elbows, a 90-degree elbow, you have a loss coefficient. If it's flanged, in other words, if you have a nice smooth transition into the elbow and out of it, then it's a relatively small number. If it has a threaded fitting on it, you can imagine that that wouldn't be so great for the fluid going through it, and it turns out to be larger. If you have a long radius, the acceleration is more gentle, so you'd expect this to be smaller than this one here, not surprisingly. And if it's only 45 degrees, then also you'd expect it to be less than 90 degrees. So all very rational. If you have 180-degree bend, again, threaded and flanged is different. If you have a T, and so I guess a T means the fact that this might be closed off, so there's no flow in here, but it's flowing past it, then there's still a loss as it goes across this little hump and past here. You could imagine it's just not going through a pipe that's closed, and so it's just disrupting the flow slightly. And of course, if that T happens not to be closed, but is actually kind of like an elbow, a 90-degree elbow, because it's not flowing here, maybe because it's closed, this would be stagnant water, and so this should be close to being like an elbow. And so this is 0.2 in this particular case, and I guess it was 0.3 here, and so you see something slightly different. And I guess you could even imagine it as the unions being threaded or so in plastic house pipes, I guess, PVC, they're put together, they're glued with a collar around it, so there is a little gap, I guess, in the pipe here as it goes through here, and so you see some small amounts of loss coefficients as a result of those. And so you could imagine just using that as a tabulation to figure out what's going on. Other thing is fittings, and so if you have fluid coming in to an open fitting, obviously if it's a closed fitting it stops here and doesn't go anywhere, but if it's open it would go through the fitting and out the other side, and I don't know if these are valves, I guess that's what these would be. A globe valve I presume is something that I actually don't know what these are, I'm not a plumber. So you could imagine different kinds. If you have a valve where this flips up as you go through, then the fluid would have to come around. I guess it wouldn't do that. The fluid would go through this fitting and then out the other side. And so it's really just depending on how disruptive this flow is to passing from one side to the other as to what the magnitude of this value would be. All right. So that's kind of the lowdown, if you like, on different valves. So I don't know whether I'll write this or whether I'll draw on something that I've written in the past. Maybe I'll just go through some examples using this. So if we go back to what we had before, so what we'd like to do is just do a simple example in terms of these magnitudes of now major losses. So in other words, we made the point that it matters whether you're on this side of the graph or this side of the graph because you solve the equation slightly differently. In either way, typically if we avoid having a pump in the system, we can define this head loss as being just this equation. So to solve this equation, it matters which side of this line we are. So let's try solving an example that straddles that. So this is the deal. Perhaps I will remove these because we can come back and do this afresh. Okay. So maybe if we're doing this, the only thing that matters. So I've made a big deal of this transition between laminar to turbulent. And I don't know if it's 2000 or it's 2200, it doesn't really matter, it's of that order. And I suppose if we come back to this, we can see that we kind of have three regimes. We have a laminar regime that kind of peters out after this. We have a fully turbulent regime that's with these horizontal lines. And we have a transition between these that is this transitional regime, which is kind of mixed laminar turbulent. The features of this, as we said before, are that these are rough interiors of pipes. These would be smooth interiors of pipes in terms of this value of epsilon. It's indexed relative to the diameter of the pipe. And I guess the other thing which might be worthwhile mentioning is that we're kind of relating a pressure drop to as a function of Reynolds number, length over diameter. We talked about dimensional analysis, right? And relative roughness. So last time we went through the idea that if we have 7 variables, pressure, length, diameter, roughness, velocity, viscosity, density, I think they probably were, then we can divide those 7 variables with 3 mass, length, and time into 4 7 minus 3 dimensionless variables. And those dimensionless variables are replicated in an Euler number, a Reynolds number, and 2 characteristic dimensionless lengths. Length to diameter of the pipe and the relative roughness. So the point of mentioning that is that for fully turbulent flow, the friction factor is a function of relative roughness, right? Because these values here are different lines based on the magnitude of roughness, but it's not a function of Reynolds number. So that's the key issue. For laminar flow, and I've already lost space, if I do the same, then the friction factor is equal to a function of, it's not a function of relative roughness, but it is a function of Reynolds number. So these are the two contrasting behaviors. And so it's important to maybe put that in your mind. This non-dimensional parameter here is equivalent really to what we're calling head loss. Pressure upstream, pressure downstream. If there's frictional loss in the pipe, then the downstream pressure is lower because it's working against friction. That's the head loss. It's the height of water from the upstream tank to the downstream tank is physically what it is. And the length of which it travels in the diameter pipe in which it travels is the length to diameter ratio. So this is the Moody chart that we'll use. So this is a portrait. Laminar flow, turbulent flow, and some transition. I guess the other thing that's important to realize is that in this transitional region, this is the curve for smooth flow down here. So anything that is a pipe that's absolutely smooth comes along this curve here. So that's a very convenient one to use for tests and things, just because it's easy to pick off if you have to pick up. Obviously in a test, you want everyone to have the same answer, and you only get the same answer if you really define well what you want. Okay, so the other thing is then that we haven't mentioned it, but these solutions go into three different categories, not 5 different categories. This is from a previous year. I can take these out. And so what we'll do today is the first category, so-called type 1. But the idea is this. If I point out the key features of this and just use a different color. So the idea here is that if we're defining the flow within a pipe, these are the three categories of variables that define the flow. The geometry, the diameter, the length, and the relative roughness. So I guess it's three parameters: diameter, length, and roughness. Diameter, length are divided by each other, and so is relative roughness, but with diameter. The flow rate's defined either as a velocity in the fitting or a volumetric flow rate. If you know the cross-sectional area, you can define either one. And the pressure drop that goes across the system, either delta P or H sub L. And so those are the variables that we can define. And so within these categories, we can define type behaviors. And I guess the type behaviors are exactly this. They're called type 1s, type 2s, and type 3s. I guess it's sometimes easier if I write these. But type 1s are where you know the velocity that's flowing, so like the jet lev. You know the diameter and length of the piping and what it's made of, so you know this. And you want to know what the pump, the head loss is, or I guess you'd also want to know what the pump magnitude would be. That would be not equals, but those would be the parameters you want to. So these are the easiest ones. These are the easiest ones because you absolutely know what the flow rate is or the velocity. If you know the flow rate and the areas, you know the velocity. So these are the easiest ones to solve. And actually the ones on the midterm are exactly that kind. Type 2 is a bit more challenging because what you know is the geometry of the piping in your house. You know what the pressure drop is between the height of the tank in the attic and the elevation of the taps or the faucets in the downstairs, but you want to determine what the velocity is. So you know the head loss, you know the geometry, but to be able to calculate the head loss, you need to be able to calculate the velocity, you need to know the friction factor, and the friction factor is a function of the velocity, which you don't know yet. And so you need to be able to determine that. And then the third type is where you know the flow rate you want, you know the pressure drop you want, but you want to dimension the pipes. Is it a big diameter pipe? Obviously you want a big diameter pipe if you want to pump things easily, but you probably will pay more for a big diameter pipe, and so there's a certain optimization that goes on. And so in types 1, 2, and 3, what you don't know is the velocity. And so if you don't know the velocity, since the friction factor is a function of the Reynolds number, which is a density, velocity, diameter, and a viscosity, if you don't know this, you don't know quite where you are on this chart. So that's the deal. So type 1, and probably a good job that I'm not writing down. So all we're trying to do is calculate exactly what the flow rate along a pipe is. The pressure drop would be delta P. This is the same as HL, so if you use Bernoulli, velocity 1 and velocity 2, upstream and downstream are the same, so those terms drop out. The elevation, Z1, Z2 are the same, those terms drop out, and you're left just with the pressure drop between upstream and downstream over unit weight. If there's no pump head in the system, you're left with this being equal to the head loss, and we can define the head loss as equal to this term here. This would be the velocity in the fitting, which is the same as V1 and V2. They're the same here by definition, if the pipe has the same diameter. And so this is the calculation. So if we do it first for the system, we need to know what the Reynolds number is. And so I just chose some numbers here. Let's have a pipe that's 1 meter long. It's a centimeter in diameter, 10 to the minus 2. And so we can calculate the Reynolds number as being the velocity times the diameter times the density of fluid times its viscosity. If we write this as velocity being unknown, then we know everything else in this. We know this is a centimeter, 10 to the minus 2. We know the density of water is 10 to the 3 kilograms per cubic meter. And we know that this, you might know this is roughly 10 to the minus 3 Pascal seconds. Newtons per meter squared seconds. And so that's exactly what's written here. So 10 to the 3, 10 to the minus 3 is 10 to the 6, times 10 to the 2, so this is 10 to the 4, multiplied by velocity. So we have Reynolds number defined as a function of velocity. And so if we want it to be laminar, well, I guess I could have left that. Stop doing this. So if we want it to be laminar, we want the Reynolds number less than 2,000. So if we wanted it to be less than 1,000, then I guess 10 to the minus 3. Actually, this is no good, right? This needs to be 10 to the minus 1 would give us 1,000 for this Reynolds number. So yes, well, 1,000 is kind of boring. I guess let's look on here. See, yeah, okay. Well, actually, 1,000 is quite convenient. Let's do that. So let me choose the numbers here that we're going to use. So let's use 10 to the minus 1. This will make this 10 to the minus 1. And this will make this 10 to the 3. If this is 10 to the 3, then what we can do is we can go up here. It comes out, if you zoom in on this, to be, this would be 0.65. It's actually not a very well-drawn graph, is it? Because we know that this should actually be 0.064. I guess this is probably 0.066, just from looking at it, right? The reason we know it's 0.064 is because we know for laminar flow that the Reynolds number, I make this smaller, so the friction factor equals 64 over RE. So if Reynolds number is 1,000, this is equal to 0.064. So that's the equation of this line. We derived it last time. So not to get too pedantic about this, so if that comes out to be what we use, if this is equal to 10 to the 3, this is equal to 10 to the minus 1 in this case. So I should get rid of these and put the right numbers in just so we can have it. Let's put the right numbers in it and do the calculation. So what is this? This velocity is equal to 10 to the minus 1 squared. This friction factor is equal to 0.064. Update Canvas for your email that you get at midnight tonight is the thing that just came up. The diameter is 10 to the minus 2. Gravity is roughly 10, right? 9.81. Length is equal to 1. And I don't know what that comes out to. Are these the right numbers here? 10 to the minus 2. This would be 10 to the minus 1 squared, which would be blah, blah, blah. So the head loss is some number. That's really all that comes out of it. It's actually much simpler than that, but I could have done it. So the other term is if we want to work on the other side. So the point in this is that we can calculate the head loss directly because we know the velocity. If we want something to be turbulent, then we want to be somewhere on this side. So I don't know what number I chose. To be greater than 1,000, if we use 1 meter a second, then the Reynolds number is equal to velocity times 10 to the 3, which is equal to, was it 10 to the 4? Yeah, 10 to the 4. Which is equal to 10 to the 4. So if it's 1 meter a second now, then the Reynolds number is 10 to the 4. If it's a smooth pipe, then what do we get? We get this. .03, that may be the number that we use. So this would be the number here. And if we use that here, do I do that? Yeah, fine. So if the velocity now is equal to 1 meter a second, this is the magnitude here. This value is 10 meters, 9.81 meters per second squared. This value is 1. This is equal to 10 to the minus 2, 1 centimeter. And if it's a smooth pipe, then the friction factor is 0.3. and you get something out of it, which is, by doing that calculation, I'm not quite sure what I'm doing here. If the roughness is equal to 1 over 100, so if the roughness is equal to 1 over 100, 1 over 100 is here. So just so you can see what I'm doing. So what did we have before? The number was, what was our Reynolds number before? Oh, it's this one, right? 10 to the 4. So if it's this, then it'd be this curve here. Looks about right. If we zoom in on this, this is 0.04, 42, 4, 6, 8, 10. So 0.042, roughly. Hopefully that's what we use down the bottom. Put that in the equation. If you fill up this, it's this here. And then as a function of this is now the velocity, which is equal to 1 meter a second all squared. This is equal to 10, this is equal to 1, this is equal to 10 to the minus 2. This now is equal to 0.042. And apparently if you calculate this out, the head loss is equal to 0.2 of a meter. And so we end up with two values. This is in millimeters. So 0.2 of a meter would be 200 Stop it. This would be equal to 200 millimeters. And so you see the contrasting flow. If you're trying to push fluid along at 1/10 of a meter a second, very slowly, kind of creeping flow, it's in this laminar regime. You go through this calculation and you come out with a magnitude of the friction factor, and you calculate a head loss across the system of 3 millimeters. If you're trying to push it 10 times faster, then you end up with a head loss which is equal to roughly 80 times that, right? 3 into 200 goes something like 80 times. And so, not surprisingly, if you're trying to push it faster along, the head losses are larger, and you would have to provide more power if you had a pump providing that motive power to move it along from one side to the other. So I guess the final point would be to make that this motive power can be provided by having your pipe, which is in the system like this, where you're going from upstream at some pressure which is the head loss between upstream and downstream, or the pressure at this point could be 0 atmospheric, and it could be 0 atmospheric here, and instead you could have a pump within the system which is supplying exactly this head loss to drive it along. So the fact that you're getting a flow rate is either driven by the fact that you have an upstream pressure which is doing that, or you have a pump which is driving it along, or I guess you could think of it by the fact that this pump is providing this head at the upstream end to be able to move it along the pipe. That's physically what you're doing. So if you had a pump here that was pressurizing a tank, then it would pressurize the tank to this pressure, and it would be they're kind of equivalent to each other. So that's kind of it. So I don't know how garbled that has been or not, but I think the important thing to realize is that when we're looking at pipe flows, the easiest ones for us to solve are the categories where we know what the velocity is. And the reason for that is that we can go straight away to this chart and we can solve in one step for the velocity and get the friction factor directly in one go. If we don't yet know what the velocity is, then we have to guess a velocity, go to this chart, see what the friction factor is, calculate the flow rate, calculate the velocity from that flow rate, and then go back to the chart if the Reynolds number doesn't match up. And so it just gets a bit more difficult. And so we'll do those next week. And I guess the other important thing to realize is that actually, if the flow is turbulent, it really doesn't matter what the Reynolds number is after you're past a threshold, because the friction factor for Reynolds number of this magnitude is the same as the friction factor for a Reynolds number of this magnitude. So long as your flow is fast enough and that you're in this regime, then life is much easier in calculating the flow through the system, because the friction factor doesn't change as a function of flow velocity. So it doesn't matter. All right, we're 1 minute over. So thanks for coming out. Oh, we do have more than 8. That's great. Good seeing you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Way to go. Okay.